Welcome back. So, we are discussing the topic of power and performance, and thermal effect has a direct relation. So, it becomes very important to understand the effect of temperature rise or thermal effect on the semiconductor. Let's go through some basic concepts, and in this presentation, let's also understand the effect of temperature on the silicon and its power and performance. So, as the temperature rises, it affects certain basic properties of a transistor or MOS device. Okay. First property that gets impacted is the energy band gap. Okay, the band gap decreases with the increase in the temperature. The band gap decreases, and as the band gap decreases, ultimately the threshold voltage decreases. Okay, so the temperature is rising, my threshold voltage of transistor is reducing. We will see the collective effect later. First, let's understand the basic properties, what's happening with the increase in the temperature. So, Vt decreases with the increase in the temperature. Carrier density, so basically there are some regions of operation in the transistor, and this curve shifts to the left side as the temperature increases. So, some of the extrinsic region becomes intrinsic region, and the carrier density, which is like thermally generated carriers, they exceed the number of the carriers which were there as a dopant generated carriers. So they will have the thermally generated carriers will dominate the dopant carriers which are there with the increase in the temperature. So okay, Vt reduces with the increase in the T. Carrier density is also impacted, and the major factor, one of the major factor is the carrier mobility. Okay, so there is some complex dependence for carrier mobility. There in certain region of temperatures which are normal temperatures, mobility decreases as the temperature increases. Okay, so but in the low temperature regions, the mobility will increase with the increase in the temperature. So so in the different regions, there are two different effects are being seen for the carrier mobility in a semiconductor devices. Okay, at the higher temperature or normal temperatures, mobility will decrease with the increase in the temperature, while at the very low temperature side, mobility will increase with the increase in the temperature. Okay. Leakage current increases exponentially with the temperature, we know as of now, and if there are some metal interconnect, its resistance will increase with the increasing in the temperature, right? That's the metal property. So in the net effect, what is happening when the temperature is increasing, the threshold voltage decrease. Let's think in the term of the transistor current. Okay, ultimately what is happening to the transistor current as the temperature increases. So Vt fact is that the transistor current will try to increase, and the carrier mobility at the high temperatures, let's talk about, the carrier mobility will try to reduce the current. So these are both opposing or forces working against each other, and the net effect will be that there will be two regions that will exist. Okay, and one is called normal dependence region, ND region, and another is called reverse dependence region. Okay, in the normal region, what happens that the net effect is that with the increase in the temperature, my drain current decreases, circuit becomes slower. Okay, in the reverse dependence region, with the increase in the temperature, the current, drain current increases. Okay, the circuit becomes slightly faster in the reverse dependence region when the temperature increases. Okay, so here we are the same facts we are trying to elaborate a bit more over here, right? So with the in our operating region, right, now operating temperature regions, so mobility threshold mobility decreases with the increase in the temperature, threshold voltage decreases, and the saturation velocity also decreases, and they have the primary impact did by dt Vsat is one factor, and did by dt Vt, this tells about the change in the id with the Vt, and did by dt Vsat is more prominent in the normal region, and that's why overall current decreases with the increase in the temperature and circuit becomes slower. And this also, like as the with the gate overdrives, means the gate to source voltage which is slightly higher than Vt, and then in that case furthermore the di by dt for saturation velocity, this becomes more prominent, right, this factor. So ultimately with the increase in the temperature my current reduces and circuit becomes slower in this region, while as the applied voltage is less and it is more close to Vt, the Vt effect becomes more prominent. Okay, so when the Vt effect becomes more prominent, then with the increase in the temperature, as the Vt goes down, the overall current increases. So that is called reverse dependence region. So two dependence regions do exist. Okay, so when someone asks what is the net effect of increase of temperature on the silicon, that actually depends. There are so many depends. So let's understand this. This figure here shows on one axis there is a temperature, on one axis there is a current, and this third axis shows the voltage. Okay, so what we see that at the lower voltages, here this area, as the temperature is increasing, right, the current is increasing. Okay, so this is reverse temperature dependence region, RD region, below these blue strips. Okay, so again the PMOS and NMOS has slightly different behavior, but the concept is same. Okay, so this one is for PMOS and this one is for NMOS. Okay, and this blue strip, upper blue strip is for NMOS and lower blue strip is for PMOS, and this is the place where the transition happens from reverse dependence regions to normal dependence region. In normal dependence region, what is happening? As the temperature is increasing, the current is slightly decreasing. Okay, so that is the normal dependence region. And what has been seen that further as our technology is scaling and high K dielectrics use, the net effect has been seen that this blue strip is nothing but that rollover point, right? It is shifting more and more towards normal operating region. Okay, so what happens now in this case, when the circuits are operating, they are sometimes operating in the normal operating region, and at times they are operating in the reverse operating region. So it becomes very unclear whether what is the net effect with the increase in the temperature, because circuit might be operating in either of these two regions, as because of this rollover point is further become higher, right, on the higher voltage side with the latest technology developments. So what is that? Okay, one more point that I wanted to touch upon was that in the normal operating region, right? So in normal operating region, as the temperature rises, in normal operating region, as the temperature rises, so circuit delay, because the current reduces, right? So delay increases more and more. So at certain point of time, it becomes inoperable at the certain frequencies as the temperature keeps rising. Okay, but in case of reverse dependence region, means in this side, what is happening here? In the reverse dependence region, as the T rises, my I rises, circuit becomes faster and faster. Okay, so it becomes more important to protect against thermal runaway in reverse temperature dependence, because as the temperature will rise, circuit will tend to become fast and fast, and that might go into the thermal rundown. So those needs to be taken care, and There are thermal mitigation schemes that we will see, but this is one of the concepts that we need to understand. In the reverse temperature dependence region, thermal runaway needs to be taken care. So what is the net power with the temperature, right? So as we know that there is a leakage power. Leakage power always increases with the temperature rise, right? And that is often the dominant factor as well. That again depends on many factors. How much control or has been put in place in the design for leakage. But net effect usually is that leakage power with the increase in the temperature, this is the dominating factor. While the other factor, as we can understand, in the normal operating region, with the increase in the temperature, delay increases, so circuit becomes slower. Okay, so when circuit becomes slower, basically for the same operation, same throughput or same performance, we will have to increase the power, right? So P will increase, and anyway the leakage is anyway increasing, but on the dynamic power side also, for keeping the same performance, you might need to apply slightly higher voltage, and you will end up dissipating more dynamic power, right, for the same performance. While if you are in reverse temperature dependence region, right, so the circuit becomes slightly faster. So the dynamic power side will be reduced as the temperature increases. But again, overall power increases only because leakage has been a dominant. Leakage is anyway increasing with the increase in the temperature, and is the dominating factor. So far we understood the effects of temperature rise in the silicon, and now we need some means to manage that, and for that we have temperature sensors which are placed in the SOC, and temperature sensors are usually based on BJTs and base emitter voltage. So we can this figure illustrates one implementation where two different diodes represents a VBE voltage, base emitter voltage. Okay, and that there is one equation that we don't need to go dive into, but ultimately it says that this construct gives that the difference between the VBE1 and VBE2 will be proportional to the temperature, and that is converted from with the ADC, and we get a digital data. Then again this needs to be characterized. Calibration needs to be done for these sensors to so that we get the digital value of that temperature again, and we calibrate this for a range of temperatures, and what are the ADC values for that, so that at runtime we can know what is the temperature. And these temperature sensors are usually placed in SOC at multiple points and close to the places where highly likely there will be more heat dissipation, yet like CPU cores. Okay. Then there are some thermal mitigation schemes are deployed. So when temperature rises, and there will be schemes to bring the temperature back down, and in some cases some clocks are being skipped or duty cycle changes happen, and in certain cases the frequency itself will be reduced from the clock circuit, or in some cases when there are critical temperature where circuits can burn or damage, and with those signals the entire system is shut down also happens. So these are the type of thermal mitigation schemes which are deployed. So yeah, I think that concludes the effect of thermal or temperature on the silicon and how we mitigate that. And we take a little pause over here, and then in the next chapter we will understand so far whatever concepts we have understood, how we apply them with the use of multiple clock and power domains in the SOC. Okay, thank you.